break. And let's start with your questions first. I'm also going to share the lab manual. Do you have any questions for me? Let me bring to experiment 17 first. Okay, your questions first. No questions? Okay. If you don't have questions, I'm going to go over the experiment 17 first. It's an introduction to IR and NMR, and experiment 18 is use of physical property trying to start or initiate identification of unknown. I don't even pretend to cover IR and NMR in one chapter, one setting, one experiment, but this is just introduction and trying to see how we are using IR in our experiments. IR can be used to identify functional groups. We can use IR to determine if the compound is pure or not, based on the location of the peaks that it's specific to reactants and product. And we are looking for kind of point of a difference between the IR of reactant and IR of product. The infrared region, which is like 4,000 to 600, or to make it simple, I usually say 400 to 4,000 per centimeter. It's sorry, per centimeter. When the light in that region is shined to the compound, is going to stretch the bonds, and when the bond is stretched, the dipole moment of the bond is going to change, and recorder from the IR machine is going to calculate how much energy was absorbed and in what region the energy was absorbed to change the bond length or change the polarity. And as a result, is going to be signal, and the signal, it translates to type of bond or the functional group. So if we know the location of different functional group, and these are some of the other terms also based on the narrow signals, broad signals, signals that is wide or broad, and if it has a peak or not. If for weak signals, it's basically the height of the signal is used to determine if it's weak or strong. Strong signals is coming from bonds that they are more polar, like a CO bond, like a CN bond. These are the bonds that are polar, and it shows like a stronger peak, because change in the bond length is going to affect significantly in changing the dipole moment of that bond. So if we know the location of different functional group, then we can predict where should we see the signal, or if we have the IR spectrum, based on the location of the signals, then we can predict what type of bond exists in that compound. So if we have the compound and we know the compound has a CO double bond, CO double bond would appear anywhere between 1600 to 1800 in the IR spectrum. And it depends on if the CO double bond is attached to electron withdrawing group, like here, another O, or if it's like a acid anhydride has electron withdrawing group attached to it, or if it's attached to just the alkyl group, or if it's conjugated. So it's going to appear between 1600 to 1800, but conjugation would lower the frequency, resonance would lower the frequency, electron withdrawing group is going to increase the frequency. Now, if we know these locations, then we can predict what we have. So location for the CO double bond for carbonyl from carboxylic acid is anywhere between 1700 to 1800, so more of like a 1715. But at the same time, you get a secondary signal that is coming from the hydrogen, from the OH of carboxylic acid, a peak between 2500 to 35, very broad peak, and that is like a significant only to, or specific only to carboxylic acid, because for alcohol and for amines, you do have a peak for the H at 3300, but is not as broad as the carboxylic acid that is going from 2500 to 3500. The resonance for amide is going to lower that signal for CO double bond to 1640, 1650, and that's because of the resonance. Pair of electron on nitrogen is going to be dropped in. Pi bond forms, double bond forms here. This pi bond goes over oxygen, so you are going to have a second resonance. So when you have a resonance, that frequency is going to drop significantly and is going to be less than 1700, and definitely like if it's going to be around 1650, 1640. And then if you have the NH with two hydrogen attached to the nitrogen, you get two peaks. If it's a primary, for secondary, you get only NH, and that you get like one peak. And if it's tertiary, so there is like a pattern that would say is going to be primary, secondary, or tertiary. For aldehyde, the CO double bond would show a peak at 17 to 80 from the 1680 to 1750. And these numbers are, again, they are not a fixed number. You always get a range, and depends on if it's attached to, if it's conjugated, or if it's attached to electron withdrawing group. It could be at the higher end or lower end. And with that peak, you also get this hydrogen, two signals at 2700 and 2800. So you get all three of them that would say you have aldehyde. So it depends on the location. So basically, you have to memorize and know the approximate location for this functional group. And then we have OH and NH. OH from alcohol around 3300 or 3200 to 3400, but is a broad peak. If you have amines, the peak is going to have the broad peak, but broad signal, so you would get the absorption, but at the same time you are going to get double peak if it's an NH2. If it's an NH, is going to be a single peak. You also have a CN bond that would appear a strong peak because CN is polar, and the peak appears between 1200, around 1200. There is a typo here, and I'm going to actually extend the deadline for the lab notebook to midnight today. And if you didn't catch this, because a couple of you, and thank you for letting me know, and I actually I checked my notes, and I saw that I also already have the notes to fix it. That the terminal alkyne and nitrile is a CN triple bond, so it's not a CN double bond. So please make sure if you copy it without paying attention that it says terminal alkyne and here it says a CC double bond, go back and change it, please. So all these double bonds for 3 is going to change to triple bond. So CN triple bond, CC triple bond, and here is the CC triple bond for terminal alkyne, and this for nitrile is going to be CN triple bond. The C and triple bond would show peak around the signal around 2200, and CC triple bond also same. The hydrogen from terminal alkyne would have a peak around 3300. So just make sure that this is a terminal alkyne, so is a triple bond attached to it. The editor who edits the lab manual, when after I give my my corrections, I had them. I checked it, and they have the notes that is supposed to be triple bond. They didn't write it correctly, edit it correctly, and unfortunately, I didn't catch it when they gave me the final proof. And I should make sure to fix it for the next edition. But manually fix it in your lab notebook so you don't have the wrong information in your lab. If the compound is aromatic or not, we can look for the signals again for around the 1400, 1500. You get two signals between 14 to 1600. And if you have a double bond, you get a signal for CC double bond at around 1600, 6 to 1660. And then you also get a signal for hydrogen that is attached to CC double bond, which is known as the vinylic hydrogen. Okay, vinylic hydrogen would show a peak over 3000, anywhere between 3000 to 3100. So you know that you have a sp2 hybridization. Any questions? Just want to make sure that you don't have any questions at this point, and also this is recording. Okay, perfect. Okay. So based on the location and the shape of the signals in IR, you can determine the functional group. IR is very strong for determining functional group. It can be used to monitor the reaction. Like for experiment 15, if the reactant is ketone, so peak at 1700 is specific for ketone. The product is alcohol. A peak at 3300 is specific to the alcohol. So we can take the IR of the reactant and product and compare and monitor the reaction. So if the peak at 1700 disappears completely, that means the reaction is complete. Or if there is no peak at 1700, that means there is no impurity of that reactant in the product of the. There is no impurity of the ketone. It can help to determine the structural formula of the compound, because if you know the functional group, you have the molar mass. It's like those are two major pieces of the puzzle that you can put together in order to find out structure formula for your unknown. Someone has a question? Victor, you have a question?
I don't, doctor. I was gonna ask a question, but then I just ratify what you said in my head, because you said if there's a peak at 1700, there is no the ketone, right?
A peak at 1700, that means that there is ketone. Yes.
Exactly. So for a moment I heard impurity, and I'm like, no, I think she said no impurity. That was all.
Yes. If
Thank
there is no peak, yes. Good. NMR. I don't know if NMR has been covered or not in lecture, but we are also, for the NMR, we are only using some of the points of the NMR that it pertains to a reaction. Let's say if we take the NMR of the product that is alcohol, we are looking for a short, broad peak anywhere between 1 to 7. The scale for NMR is different. It goes from 0 to 10. And for the NMR, both for NMR and IR, if you have the structural formula, is going to help you to look at the type of hydrogens. So if you have the type of proton and you look at this table, it's showing at what region you expect to see a signal between 0 to 10, and the outer scale part is for carboxylic acid, which is 10 to 13. Now, you can use this NMR spectrum and eliminate choices. For example, if you see a signal between 9 and 10, you definitely have aldehyde. No other functional group or no other type of hydrogen gives a signal between 9 and 10. A carboxylic acid would have a signal outscaled. That means between 10 to 12 or 10 to 13, but it's outscaled. So if all the signals are between 0 and 9 and nothing between 9 and 10, that means you have no aldehyde, you have no carboxylic acid. If you have a peak between 7 and 8, again, here it says 6 to 9, but 7 and 8 is the most common area for aromatic hydrogen. And if you say ARH, that means this hydrogen is directly attached to the benzene ring or the aromatic ring. It's part of the aromatic ring. So this hydrogen is an aromatic hydrogen. It's not a group that is attached to it. So if there is a peak between 7 and 8, you definitely have a benzene ring in your compound. So it kind of eliminates lots of choices. If you have a peak between 4 and 6, that means you have vinylic hydrogen. What is vinylic hydrogen again? You have a carbon-carbon double bond, and one of the carbons that carries the double bond also carries hydrogen, and that hydrogen is known as vinylic hydrogen. Then you could have allylic hydrogen. Let me see if we have the allylic hydrogen here. Here is allylic hydrogen. Allylic hydrogen is a hydrogen on a carbon adjacent to carbon-carbon double bond. So if you have allylic hydrogen, you would have a signal around like 2 or less, between 1.5 and 2. But if it's vinylic, it's going to be between 4 and 6. So based on the location of the peak. Now, if you have a CH3, that's for alkane, CH3 would have a peak around 1. That is a primary carbon. But if you have a CH2 or a secondary carbon, that means this carbon is attached to 2 other R group. And R group is just a simple version of carbon chain in this table. Then is going to be secondary carbon would have a peak between 1.2 and 1.4, so slightly higher. If you have electron withdrawing attached to the same carbon, it's going to shift to higher number. Like if you have chlorine attached to it, it's going to go to higher number. Bromine, same thing in the electron withdrawing group. Yes, question.
Doctor, that's what I did in my pre-lab quiz. So I typed it first. So I noticed, like for example, 2-pentanone. That was, I believe, question 3 or 4 on the pre-lab quiz. As you get closer to that ketone in 2-pentanone, the CH2s will not have the same value because, you know,
exactly,
because distance is a factor too for withdrawing electrons. So
exactly, very good.
That I just gave you like increments. I don't know if that's the exact one when you measure it in the lab, but I just, obviously, if the one furthest away was, I don't know, a certain number, I bumped the other one up by 0.4 or 0.3. So you could see that I at least rationalized that there's a difference because of the
perfect. Perfect. Yes.
But I don't know if those are the good numbers. It's within
no, it's good as long as like for CH3 that is attached to carbonyl group, which is electron withdrawing group, you don't give that 1 because
no.
1 would have been if it's attached to alkyl group or another carbon, a simple carbon, no carbonyl group. Any electron withdrawing group is going to increase, and I don't expect you give me exact location for it. It's just approximate location, as you said. If it's you know, you have to use the rationale and try to predict like approximate location. That's perfect. That's great.
Okay, but once you have that electron withdrawing group, and let's say it's immediate to it, it'll be pushed beyond this range. So for RCH3, it will be beyond 1 always.
Exactly.
Okay.
Yes.
Thank you.
Very good. Perfect. So if you have electron withdrawing group attached to it, it's going to shift to higher number. Like you have a oxygen attached to this carbon, is going to shift to higher number. And or bromine or chlorine or another, like you have this oxygen attached to this CH3, carries the same carbon carries it. And if it's not the same carbon, if it's the adjacent carbon, it's going to shift, but not as significantly. Like the jump here is from 1 to 3.7. That's like by 3 units is jumping, is moving up. But if you look at this one, because oxygen is not attached to the same carbon, is attached to the carbon that is connected to this carbon, is just going up by 1.2. So the effect is less significant. The more distance is between the electron withdrawing group and the hydrogens that you are concerned about, the less of the effect is going to be. So
I see it. Thank you.
If it's attached to the same carbon, the effect is more significant. The number of signals, like how many different type of hydrogens we have in this example?
I count 2, CA.
Yeah. You see, like the NMR spectrum, it gives you 2 signals, and that means you have 2 type of hydrogens. So it goes both ways. Or if you come and identify your hydrogens, you see that you have a CH3 hydrogen that is not aromatic, and then you have all these hydrogens that they are aromatic. The aromatic hydrogen would show a peak between 7 and 8. That's what we have here. And then the CH3 is supposed to be 1, but CH3 is not plain CH3. This is attached to a pi system. Pi system is electron withdrawing group for NMR. So it's going to shift to higher number, and you get a signal between 2 and 3. So this hydrogen is called benzylic hydrogen. Remember, allylic hydrogen, benzylic hydrogen, vinylic hydrogen, these are attached to pi system, or they are adjacent to pi system, and they are going to appear at the higher number than the predicted plain alkane. So the CH3, if it's alkane, if it's attached to another open chain carbon, it would be at 1, but since it's attached to aromatic ring, it appears at 2, and we have 2 signals. So number of signal in NMR corresponds to number of different type of hydrogens. Another example, another concern or piece of information that you get is the splitting pattern. For this CH3 on the left side, what would be the splitting pattern? To determine the splitting pattern, you don't count how many hydrogen you have on that carbon. You count the adjacent element to see how many hydrogen you have on the adjacent one. So there is no carbon, adjacent carbon. As a result, there's no hydrogen there. So you have 0 adjacent hydrogen, or 0 hydrogen on adjacent carbon, and number of adjacent hydrogen on adjacent carbon plus 1 is the pattern. So what is the splitting pattern for this CH3 that is highlighted now?
Singlet.
It would be singlet. Okay, very good. And then the CH2 that is attached to the oxygen, what would be the splitting pattern for the CH2? And what are we counting? We are counting the number of hydrogen on the left side, number of hydrogens on the right side. You count all neighbors. On the left side, there is no carbons, so there is no hydrogen coming from the left side to count. On the right side, we have 3 hydrogens. And if we have 3 hydrogens, 3 plus 1 is going to be 4. And that's why we say quartet. So we are going to have, for CH2, we will have a quartet. What about the CH3 on the right side? The CH3 that is highlighted. CH3 on the right side.
Triplet.
What would be the splitting pattern for that one?
Triplet.
a triplet because on the adjacent carbon you have 2 hydrogen, and the 2 hydrogen plus 1, it will be a triplet. When you draw the signals with the splitting pattern, if you have even number of, if the splitting pattern is like an even number, like a doublet or like a quartet, you would have 2 same height in the peak in the center, and then you start going down like a Christmas tree. If it's an odd number, you would have like 1 peak that has the highest peak, and then it would go down and down the height. So if you have a triplet, we have 1 maximum height for the center peak, and then the other 2 are lower. But if when you have a quartet, you have 2 that they are same height and they appear in the center, and then start going down. Same thing here when you have like 7. Okay, when you have 7 here, septet, you have 1, because it's odd number, you have 1 that is the maximum height, and then it just goes down on the others. So this is like a tree pattern or Christmas tree pattern that is followed. When you are drawing the splitting pattern is not going to be all same height. So based on how do you use the splitting pattern, you say, okay, if there is a quartet, that means this group is attached to a CH3. If this one shows a peak that is a triplet, the signal for this CH3 is triplet, that means on the adjacent carbon there must be 2 hydrogen. And if this one shows a singlet, that means it's separated by an element like a sulfur or oxygen or nitrogen from other carbons, and there's no hydrogen on the adjacent element. So we know about the splitting pattern, we know about the location of the signal, and the last thing that we want to talk about is the height of the peak. So if you look at the height of the peak, for height of the peak is or the integration line, that shows what is the ratio. For example, in here, if we had the integration line, if for this one is like this height, okay, if that is the integration line there and represents, how many hydrogen does it represent, this blue line here, integration line? 1, 2, 3, 4, 5, right? The other signal, it represents 3 hydrogen. So the height of this blue line, which is the integration line, compared to the height of the other blue line, it's supposed to be like a 5 to 3. So you would have 3 to 5 height ratio of the integration line. The integration line is a technology that used in NMR, and it allows you not to worry about calculating peak area. The machine does it for you, and it just gives that a straight line, and you use a ruler, measure the height, and that height corresponds to the number of hydrogens you have. So if you have like a 3 to 5, then the height ratio should be 3 to 5 for each type of hydrogen. Any questions?
Is it always whole numbers, no decimals for the ratios to keep it simple?
It's the ratio, but it's not always whole number. So maybe you would like have like a 0.5 height, but 0.5 represents 1 hydrogen. Then every 0.5 in the height represents 1 hydrogen.
Okay, thank you.
Yes, you're welcome. But the ratio is always like is a whole number ratio, or you can multiply to make it whole number ratio.
To make it simple, right?
Yes, to make it simple. Because we don't have half hydrogen. So if you don't have half hydrogens, if you find the ratio of half, then you make it whole number because you're counting number of hydrogens.
Okay.
Okay, if you don't have questions from the IR NMR, I just have to tell you again that we are using experiment 17 as support for application of the IR and NMR to in other experiments. So on the final exam, you're not going to get direct question from the IR or NMR, and I'm not giving you this structure and say draw the NMR spectrum or draw the IR spectrum for this. What I say instead, like, how do you know that if your product is supposed to be alcohol, what is the new peak that would appear if you take NMR of that product? So if it's alcohol, then you are looking for a short. Why short? Because how many OH you have per molecule is just one, and you have plenty of other types of hydrogen. So the height of the peak that is coming from OH is going to be shorter. And then short and broad peak. Why broad peak? Because OH and NH, because of the hydrogen bonding, would give broad peak both for IR and for NMR. Or the example that I use, reduction of a ketone. If it's a reduction of a ketone, that means you have ketone to alcohol. So the product would have OH, the reactant is going to have CO double bond. If you look here, you have like a triplet and a quartet. That means that next to this, whatever it is, there must be a CH3. And then here we see a triplet. It means that next to this, something should have like a 2 hydrogen. So this can give like a good approximation of a CH2, CH3 next to each other. And then you have a peaks between 7 and 8. So if you have a peak between 7 and 8, that means you have aromatic. There's the aromatic ring here. You have a peak at 9. What does it mean? What does a peak at 9, between 9 and 10 means?
Aldehyde?
You have aldehyde. So it means that you have a CH2, CH3, you have benzene ring, and you have aldehyde functional group. And I think there is an answer for that.
Doctor,
yes.
Before you continue, can you go back to that one with the 2 peaks at the benzylic area, the benzylic hydrogens? So my question is, because it's very confusion for me.
This one?
Yeah, I have an exam coming up. So when you have those 2 peaks, because those are 2 doublets almost identical, and they're within the range of benzylic hydrogens. So how do I approach this to identify it when I have to like propose a structure from this whole NMR?
So if it's like a 2 doublet, that means that you have 2 identical, you have a signal from that is coming from 2 different type of hydrogen on the benzene ring.
Okay, so this is
and they
for
with each other.
so,
and one is closer to 8, one is closer to 7. So one is closer to the electron withdrawing group. The other one is close to the, it's further away from electron withdrawing group. So if you put the pieces of puzzle together, let me see if I can help you. Let's say definitely we have benzene ring, right? And the benzene ring here has substitutions, and we have 2 substitutions, right?
Okay.
We have aldehyde and we have ethyl group. If we have aldehyde and we have ethyl group, then you have a 2 and 2. And let me bring whiteboard so I can show you. Okay, let's say you have this benzene ring here. Under normal condition, when there is no what is it? Substitutions, you have 1 hydrogen on each carbon, so that gives you 6 carbon and 6 hydrogen. If you have a substitution here, substituent of, let's say, aldehyde here, if you have aldehyde and there is a hydrogen here, aldehyde is the electron withdrawing group, right? And then you have 2 identical, so you have 4 hydrogens left So this hydrogen here is identical to the hydrogen on the right side. So if I call this one A, this would also be A, right? That would also be A. This one, as you said or someone else said, that the further away is from the electron withdrawing group, less effect. So if this is a hydrogen B, this is also hydrogen B.
Because of symmetry, right?
Yes, and because how far it's from the aldehyde or the electron withdrawing group. And then you also had a methyl group attached to CH2. So we can say that the signals that we had there for CH3, this one is going to show what would be the splitting pattern for this one, for the CH3.
That's going to be a triplet.
This is going to be a triplet. This one, what would be splitting pattern? And I hope that everyone in class is trying to answer the question, because this is for everyone and I expect participation from everyone. What would be the splitting pattern for this? What are you counting? Is when you look at the benzene ring, there is a hydrogen until you add a group. So if you add a group here, there is no hydrogen. So there's no hydrogen in this corner. Okay, no hydrogen here, but there is a methyl group attached on that side. So you have 3, and this is no hydrogen from the other side. So the total adjacent hydrogen is 3, plus 1 is going to be 4. So it's going to be a quartet, right? So it's going to be quartet.
Also,
so this is going to be quartet, and that's going to be triplet.
What I know from lecture is that you have to be within 3 bonds. Hydrogens have to be within 3 bonds of each other, so they can be counted as a quartet, a singlet, like the splitting pattern. So there's a certain distance for that. And this CH2, so you go from from H2 or one of those hydrogens to carbon to the other carbon. You can make it to the other hydrogens even though you wanted to, because you would be violating.
Yeah, it's too far. The other hydrogens are too far. Yes. So hydrogen A. Can you tell me hydrogen A, is it singlet, doublet, or quartet, or triplet? Hydrogen A.
That's a doublet.
It's a doublet because there's no hydrogen here, but there's just one hydrogen on this side. So just one hydrogen is going to give a doublet. And hydrogen B?
Same thing.
A doublet. So if you have para-di-substituted, very good, Julie. If you have a para-di-substituted aromatic ring, you would get 2 doublets. If it's a para-di-substitute, you will get 2 doublets for the aromatic ring or aromatic hydrogens. So from all the information, you could say you do have aldehyde, you have aromatic ring, and you have an ethyl group. And since you have 2 doublets, that means it's a para-di-substituted. So the CH2 and the CH3, it's supposed to be just one group, because you have 4 hydrogens that are still aromatic.
Thank you, doctor, for drawing.
Okay, perfect. Okay, we're going to go experiment 18. You get a lot of questions from experiment 18 on the exam, final exam. So I want to make sure that I go over the type of questions or the information that you see from the experiment 18. Experiment 18 is the base and foundation for experiment 19, which you're going to have like 3 weeks of it, and then you work with your unknown. Based on the systematic steps that is presented experiment 18, when you get an unknown, and we are not talking about the unknown that that is coming from like it's either orthopara or meta product. This unknown, you get a test tube with like half filled with liquid or 1/3 filled with solid, a white powder or yellow powder or different color, and then you are supposed to come up with the name of this unknown. So the steps you follow, you first look for physical properties. When you look for physical properties, you look for, if it's a solid compound, you look for melting point, you determine the melting point. If it's liquid, you determine the boiling point. You record the color, you record the appearance, and any information that you can get by looking at the compound or measuring physical properties. Step 2 is you are going to check the solubility. Based on the solubility, you can divide these organic compounds in multiple groups. And you're not going to come up with a single compound, but you could at least eliminate all other groups of the compound, which is a good step. So you take the solubility test first. Can anyone tell me what does it mean if the compound dissolves in water? What's the conclusion?
I would say it's a salt. It's ionic.
Or highly polar, right?
Yeah.
Polar, the general rule for solubility is that like dissolves in like, which means that the compound has same intermolecular force as water or it's same polarity. So polar compound dissolves in polar solvent. So since water is polar, if the compound dissolves in water, that means it's polar. Compounds that are polar, they have polar functional group like OH or like CO double bond or NH. So if your compound is aldehyde, if it's ketone, if it's ester, if it's alcohol, if it's amine or carboxylic acid, it can dissolve potentially in water with one condition. The number of carbon, if you have 5 or more carbon, is not going to dissolve. Less than 5 carbon, 5 is the magic number. Up to 5 carbon of polar functional group, it can dissolve in water. So if you have alcohol, it would dissolve in water. Less than 5 carbon. If you have methanol, ethanol, propanol, butanol, and then after that, the solubility significantly decreases. If you have a ketone, you have acetone, is a 3-carbon ketone. Butanone is a 4-carbon ketone, and after that, the solubility is going to drop. So if the compound dissolves in water, we know that is highly polar. What do you think if the compound dissolves in sodium hydroxide? What would be your conclusion? If the compound dissolves in sodium hydroxide.
Is it an acid?
What could you say? It could be acid, yes.
Okay.
That compound could be acidic compound. And the example of acidic compounds, those are carboxylic acids or phenols. If you have carboxylic acid or phenol, it would dissolve in sodium hydroxide. Basically, what it does, it reacts with sodium hydroxide. It's an acid-base reaction because sodium hydroxide is a strong base. So the acid is going to dissolve. So if you have a phenol or if you have carboxylic acid, can dissolve. What's the difference between sodium bicarbonate and sodium hydroxide? Which one is the stronger base? Sodium hydroxide, stronger base, or sodium bicarbonate? Sodium bicarbonate is a weak base. Sodium hydroxide is a strong base. Yes, sodium hydroxide is a strong base. Now, sodium bicarbonate can dissolve acids that they are stronger acids. It doesn't dissolve weak acid. It only dissolves strong acid. So if the compound dissolves in sodium hydroxide, it's either phenol or carboxylic acid. But if it dissolves in sodium bicarbonate, you know, is the stronger of the two, and that would be carboxylic acid. Phenol doesn't dissolve in sodium bicarbonate unless it's a specific phenol, with like a nitro group on it, an electron withdrawing group, and it's like is a specific phenol. But normal phenols do not dissolve in sodium bicarbonate. What about if the compound dissolves in HCl? What does it mean? What would be the nature of that compound?
Basic? The base?
That compound is going to be basic. And could someone tell me what is the example of a basic organic compound? Compound containing nitrogen, like amines, they are basic compounds. So if the compound dissolves in HCl, that means it's basic. That means it contains a nitrogen, is a CN bond, and we know that is going to be basic, act as a base, and reacts with HCl. I have chemical reactions of the solubility of the acid in sodium hydroxide, carboxylic acid and phenolosodium hydroxide in the video. Please pay attention, make sure, and I'm even asking to take a screenshot, make sure you know those reactions because at least 2 of them would be on the exam. So I'm telling you, it's already recorded here. So I don't want you get to the exam and say, I just missed that part. I was watching every bit of that experiment. I just missed that part because you get a lot of questions from experiment 18 in the final exam, and you see the type of question in the video, so make sure to watch it. No, hydrocarbons are good examples, but they don't dissolve in HCl because they are neutral. They don't dissolve in sodium hydroxide, and they don't dissolve in water. Hydrocarbons do not dissolve in anything. They don't even dissolve in the H2SO4, okay? They don't even dissolve in H2SO4. What would you do if your phone doesn't? Okay, stop. Okay, experiment 18 goes back to experiment 18. You need to know the experiment 18 and know how to deal with the solubility chart. So going to minimize it so I can fit more into this page. So you need to know what does these lines and writing means in every step. Okay, so you are going to start with water or your unknown. Try to dissolve in water, and just knowing the solubility and also for each of the solvent, and also the reaction that the one that I said know the reactions is like reaction of carboxylic acid with sodium hydroxide, or reaction of amine with HCl, reactions of phenols with sodium hydroxide, if there is a reaction or no reaction. Let's say if you have carboxylic acid, would it dissolve in HCl? No, carboxylic acid is not going to dissolve in HCl because it's acid in acid. But carboxylic acid dissolves in sodium hydroxide, which is a strong base. So when you use the solubility chart, first you start dissolving the sample in water. If it doesn't dissolve in water, you go down, but if it dissolves in water, you would go up. Okay, so if the compound is soluble in water, what type of compound it could be? You already said that it's going to be polar compound, and here are some examples of polar compound that you have there, and those are the low molecular weight alcohol, aldehyde, ketone, acid, ester, or amines, and they should be like up to 5 carbon. If it's more than 5 carbon, it's not going to dissolve in water. And if they dissolve in water, you also can check to dissolve in ether. If it dissolves in ether, you get the group S1. And if it doesn't dissolve in ether, then you can get the group of S2. We don't deal much with the group S2, So you don't have to be worried about it. Just make sure you know that these compounds, that they have like they are more polar, and they are not, they like, if they are polybasic or if they are poly hydroxy alcohols, then they don't dissolve in ether. They're too polar to dissolve in ether. But we are not, I will not test it because we don't do experiments with these. I'm not going to test it based on group S2, but S1, yes, definitely. Now, if the compound doesn't dissolve in water, then you try the sodium hydroxide. Because if it dissolves in water, it would definitely dissolve in sodium hydroxide. Why? Because 95% of the sodium hydroxide solution is water. So it kind of defeats the purpose. Why would you test your sample if it dissolves in water, again with sodium hydroxide? It already dissolves in water. That means it's going to dissolve in the 95% of the sodium hydroxide solution. So it's going to, if it dissolves in sodium hydroxide, then we know it's a basic compound. If it's an acidic compound, it could be carboxylic acid or phenol. And since we don't know which one it is, we are going to continue with sodium bicarbonate. Now, if it dissolves in sodium hydroxide and also dissolves in sodium bicarbonate, it's going to be carboxylic acid. If it dissolves in sodium hydroxide, but it doesn't dissolve in sodium bicarbonate, it's going to be phenols. And when you go down, if it did not dissolve in water and not in sodium hydroxide, then you would try HCl. If it dissolves in HCl, is a basic compound. It could be primary, secondary, or tertiary amine. But if it doesn't dissolve in HCl, is not polar enough to dissolve in water, is not basic or compound to dissolve in HCl, and is not acidic compound to dissolve in sodium hydroxide. Then what? You are going to test with sulfuric acid. We are not going to work with group X or Y, and you don't have to memorize that part, okay? There would be no question from group X or S2, group X or group Y. But if the compound doesn't dissolve in water, NaOH, or HCl, then you test the solubility in sulfuric acid. If it's soluble, you would see color change. Like you would see one phase and color change. If it's not soluble, you would see like two phases. If it's soluble, that means it has a polar functional group. It could be ketone, aldehyde, ester, or any of the ones that, or at least it has a carbon-carbon double bond. And they have higher, if it's a ketone, it has 5 carbon or higher, because if it's less than 5 carbon, it would dissolve in water already. So these are like high molecular weight usually. And if it doesn't dissolve, it could be aromatic compound, or it could be hydrocarbons. You see, the hydrocarbon doesn't dissolve in anything, like ethane, propane, or any alkane. It would not dissolve in any of the solvents. So let me ask you a question. These are the type of questions that you could also see on the exam, and you have more type of questions in the video. And I'm sure when you watch the video, pay attention to the examples that I'm using also. Let's say if you have a test tube, and in the test tube, you don't know it is propanone or octanone. Which solubility test you would use to distinguish if your compound is a propanone or if it's octanone? What test do you think it will work for you to find out if your unknown is a propanone or octanone? No, solubility test. Which solubility test you would use? You can look at the chart. If you have a propanone or octanone, what is the functional group on those two?
Ketone.
Both of them are ketone, right? How would you distinguish between the octanone and the propanone? What solubility test? What solvent you would use to distinguish? If you use H2SO4, it would dissolve both of them. Because it's ketone, it would dissolve both of them. Both of them are ketone, right? It would dissolve both of them. Okay, I give you a hint. How many carbons do you have in propanone? Propanone, 3 carbon, and octanone, 8 carbon. So what solubility test would discriminate between the two? Water. Okay, water would discriminate. Which one would dissolve in water?
The one with the least amount of carbon?
Least. Okay, it has to be less than 5. So the propanone would dissolve in the water, but octanone doesn't dissolve. So if you do test solubility with water, and if it dissolves, you know is propanol. If it doesn't dissolve, you know is octanone. Okay. Now we have another test tube that we don't know if it's phenol or is benzoic acid. What would you use? Which solubility test would you use? Phenol and benzoic acid. Sodium bicarbonate. Very good. Can you tell me what would be the evidence? How would you know if it's a phenol or the benzoic acid? Or I make it easier if you have to type so you type less. Which one would dissolve in sodium bicarbonate? And which one doesn't dissolve? The acid would dissolve in sodium bicarbonate, but the phenol does not dissolve, right? So if you have the test tube that you think is one of the two, you are going to add sodium bicarbonate. If it bubbles, basically sodium bicarbonate is going to react with benzoic acid, is an acid-base reaction, and is going to produce carbon dioxide gas, and it bubbles. So when you see bubbles, that means that you had carboxylic acid and you add sodium bicarbonate. So you see those bubbles. So if it bubbles or reacts, you know that you have carboxylic acid. But if it doesn't dissolve or doesn't react, then you know you have phenol. Okay, can you give me a compound? You could have plenty of different answers, but many of them are correct. Can you give me a compound that dissolves in water? Name of a compound that dissolves in water. Ethanol, that's the alcohol. And it will dissolve in water because of organic compounds. Sodium chloride is a salt. It does dissolve, but I should have been more specific. Organic compounds that dissolves in water. Any alcohol with less than 4 carbon. Any ketone with less than 4 carbon. Any ethylene glycol. Ethylene glycol would dissolve definitely because you have 2 carbon and 2 OH. That's even more soluble than alcohol in water. Can you give me name of acid that does dissolve in water? Name of an acid that dissolves in water. You can give me a structure or name.
Acid chloride.
Organic acid. Organic acid. Organic. Sorry.
Oh, organic. Okay.
I have to be more specific now.
See?
Yes, I have to be more specific. Organic acid. All acids, they actually, the inorganic ones, they all dissolve in water. And that's how they are defined. But organic acid that dissolves in water.
I'm not seeing it, doctor. I'm trying to find it.
Okay, when you say less than 5 carbons, so you start with like a met, right? So that would be methanoic acid. Ethanoic acid. Prop would be propanoic acid. And then butanoic acid, and it stops there. Acetic acid is the commercial name for ethanoic acid. Acetic acid has 2 carbon, and that dissolves in water, and it makes it vinegar. Okay? But if you want to say a simple compound that is acid that dissolves in water, you should have less than 4 carbon per every functional group. For every COOH, you should have less than 5 carbon. Okay, as long as you understand like how important is 18, and the reason I don't have a lab report for this is to make sure that you have the time to watch the video carefully and read the experiment very carefully, because if you don't understand experiment 18, you're not going to do well on your final exam, and that's not the time for you to be upset. It's very late, and I'm already telling you that you get a lot of questions. No lab reports. Yes. Watch the video and read the experiment. Watch the video and read the experiment 18 carefully. Yes, Victor.
Doctor, one more question. You said no more prelapse from now on?
No more prelapse.